Right. So while I'm not here this Friday, I still wanted to kind of have most of the content of that Friday review session. So this document here is in the Moodle for all the Friday review sessions. And we'll do probably like maybe 2 videos, one on this first page and then one on the mechanisms that will hopefully get you some extra practice of kind of like applying these. For each of these, what we'll do is we'll kind of walk through one question, and then I'll say something along the lines of pause the video and think about what you would answer, and then I'll kind of answer and kind of explain my rationale, and hopefully you don't just simply watch this through. Pause it and actually like kind of think about what you would say, and then if me and you agree, that's awesome. That's good signs that you're having good comprehension of the material. If you and I disagree, then really focus on that explanation and kind of see like what did you miss that would give us some extra information about that being the correct answer. So for this first one, we have looks like maybe 1, 2, 3, 4, 5, 6. There's 8. It looks like structures that have some hydrogens labeled HA, HB, HC. That A, B, and C is not an element or anything. That's just simply like a generic label. So I'm saying that HA is different than HB, which is different than HC, and that's just the easy way for me to like reference which one I'm talking to, and not like just like physically point to it because you just have me up in your top corner of your screen. And what we're going to do is we're going to look at of those different ones that are labeled A, B, and C. Some of them actually go all the way up to like E. We'll say which of these we think is the most acidic. So let's go ahead and kind of just zoom in, and we'll do the first column, then our second column. So let's go and start with the structure here. Overall, we have a total of 3 different possibilities, HA, HB, and HC. And what we want to do is we want to think about which of these is going to be the most acidic. So if I reacted this with a strong base, which would be the proton that would be removed? Go ahead and pause the video and think for a second which one you think is the most acidic and rationalize why. Now, when I'm looking at these, I see that each of these are going to be on a carbon. This right here is a carbon, this right, or sorry, that's not the right spot. This right here is a carbon, and this right here is a carbon. So they're all connected to carbon, so we tie there. So I don't have any of that kind of differentiation. So the main thing that I'm going to be thinking now is I don't see much in terms of resonance or inductive effect. I don't have anything electronegative. So this is actually going to be one that's going to fall back to our SP character, how much S character you have, thinking of our different hybridization, where A is connected to an sp3 hybridized, B is connected to an sp2 hybridized, and C is connected to an sp hybridized. And one thing that we'll remember is as we increase our S character or have less hybrid orbitals, that is going to help win out. So here, our C is going to end up being our most acidic. I rationalize that directly through thinking about my hybridization. You could also use the pKa's. And I actually do have way at the bottom a bunch of pKa tables. I'll just say the words. I guess we can look here. So sp3, sp2, sp being like the first 3 entries here in terms of our pKa's. So up here at our structure, or for HA, HA is going to have a really high pKa, around 50. B is going to be around 45, which is also wicked high. And then C is actually going to be significantly better. So C is going to win out because that's going to be our lowest pKa, or using our rules from a previous video, that's going to be our most stabilized because of the S character. Either of those rationales work. Whichever gets you the right answer works for me. Let's go and look at the next one. Here we have a 4-carbon backbone chain with an alcohol that carries HA, and then another functional group that you should be aware of that has HB. Go ahead and pause the video and think between A and B, which is more acidic and why. Now, we can approach this either with pKa or with our rationalization. In both of these, I'm going to be having that charge originally sitting on an oxygen. So we're going to tie there. So there's no major difference in the atom that hydrogen is attached to. So the next thing I'll then start thinking about is, do I have some resonance or some inductive effect? And here for HA, that alcohol is isolated. I don't have anything around it. I do single-single and single-single in terms of my bonds. So I can't do any resonance, meaning that charge is going to be localized or stuck on that alcohol. Where in the case of my carboxylic acid, that's that name of that functional group. I didn't want to say that to give it away too easily. That's going to have some resonance. So if I put a negative charge here, that can resonate up to that other oxygen. That resonance stabilization will help make B more acidic. If I approach it from a pK standpoint, pK of an alcohol is around 16, where pK of a carboxylic acid is around 5. So in terms of those kind of general comparisons, whether I approach it thinking about resonance or just purely based on pK values, both will get me my major answer, being B being my most acidic proton. Next, let's look down at our third structure. Here we have a benzene ring, that's that 6-membered ring. We have a HA that is connected to an oxygen, and then HB, which is connected also to an oxygen. Go ahead and think about between A and B, which you think is most acidic and why. Now this one's a little bit trickier because both of them are going to be on an oxygen, which will tie, and both of them now have resonance. So if I put a negative charge here, I can get resonance in the ring, and this can actually go all the way around, or here I can get resonance on my carboxylic acid. So both of these have some resonance stabilization. Here is one where knowing a little bit of pK values are helpful. Ultimately, the pK of a phenol, which is going to be an alcohol on a benzene or a phenyl ring, is going to be around 10. And we know that the pK of a carboxylic acid is around 5. So here our oxygen is going to win out. Our carboxylic acid oxygen, because they're both oxygens. Both of them do have resonance. So that's one where you got to think a little bit more. If it does help, in all the resonances of the phenol, all of those negative charges are going to be on carbon, where in our carboxylic acid, it's going to be on that oxygen, and oxygen can carry a negative charge better than a carbon. But there's ones where having a little bit of pK value helps, and like in the notes where we kind of had some examples of some pKs to kind of like think about. The phenol and the carboxylic acid are both good ones to keep on your mind, especially that the pK of a carboxylic acid is around 5. All right, let's go and look at our fourth one here. Both HA and HB are going to be an alcohol on an alcohol. They're the exact same functional group. And then I have a ketone sitting in the middle. Go ahead and pause the video and think to yourself, which of these, A or B, would you say is more acidic and why? Now, both of these are on alcohols, so they both are going to have a pK of around 16. So my pKa leaves me kind of high and dry. I don't really have much to kind of go on. So I'm going to have to use some other justification focused on like resonance or inductive effect. I do see that I have a carbonyl, but I cannot resonate with it because I have single, 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 single. I have a lot of single bonds here. But now if I look at where this carbonyl is, that is going to be electronegative, that oxygen. We're going to have a dipole associated with it. And I can see that I have a 2-carbon spacer to B, where I have a 1, 2, 3, 4 carbon spacer to my alcohol with HA. So here, we are going to get some inductive effect that's going to be stabilizing. This is going to be a pretty weak inductive effect, but that ketone is going to be closer to HB than HA, meaning HB will be more stable because of that inductive effect. That ketone is like twice as close as it is to kind of HA. So here the inductive effect for my ketone will make HB are more acidic. All right. Let's spice it up a little bit and look at this one. This is actually a really interesting one. I actually used this as a review question in my Orgo 2, and actually some students got it wrong. So this is one where I'd actually recommend you actually draw out the conjugate base for both HA and HB. So go ahead and try to draw out both the conjugate base for abstracting HA versus HB, and then try to rationalize which of those you think is going to be a more stable conjugate base. Go ahead and pause the video, and I'll check back with you in a second. So let's start by just drawing our conjugates. So I just will show equilibrium here. So this will be minus HA and then minus HB. So if I remove HA, I would have a structure like this that would now have a lone pair on this carbon and a minus charge. So this is the same general charge, just I'm removing HA. So kind of from like a mechanistic standpoint, if I had a base, that base abstracts HA, and then my lone pair goes to that carbon that A is attached to. If I do that same thing to HB, my base can abstract a proton and then give me a lone pair on that carbon. My ultimate conjugate base would look like this. So those are my two possible conjugate bases that I have. And one of our questions is, which of these can be stabilized by resonance? If I look over at my HA side, I have a lone pair next to my double bond of my carbonyl. So this one can do resonance, where in terms of my HB, I don't have any resonance because I do single-single in terms of my bonds. So if I move my electrons in here, this oxygen is now overloaded and there's nothing else I can do. So that actually gives me a dead end. So I have no resonance stabilization on that charge, while there can be resonance like with like the ester, which is that functional group there. So that's the carbonyl with the oxygen connected to a carbon. I don't actually have any resonance to stabilize that negative charge. So for here, my HA will win out, being my more acidic because of that resonance stabilization. One of the kind of biggest like hiccups here is forgetting that there's a carbon right here. I'm thinking that that charge goes all the way on the oxygen, but both of these are actually going to be on that specific carbon. So let's look at our next one. Here we have two different alcohols. HA is an alcohol and HB is an alcohol. Go ahead and take a second and think about between these two, which you think is going to be more acidic and why. Now for these, both being an alcohol means they're going to have pretty similar pKa's. However, there's actually a special term for an alcohol that's connected directly to a benzene, and we've mentioned a few times, but it's called a phenol. The ol is what comes from the alcohol, and the phen comes from this benzene as a substituent, which is actually known as a phenyl, P-H-E-N-Y-L. So that's kind of the combination of the alcohol and phenyl together to make this phenol. You'll also sometimes see like phenolic describing those alcohols directly connected to like a benzene ring. So the phenolic compounds are going to have a lower pKa than that of your normal alcohol. So your normal alcohol, we'll say, is around 16, where your phenolic one is around 10. And that's going to be because of the fact that you actually get some resonance stabilization. If you come in and abstract HA, which is going to be more acidic, and you get your conjugate base, that conjugate base can do resonance with that benzene ring, and that is going to be your stabilization. That is also an sp2 hybridized oxygen because of that resonance compared to your sp3 of your 1 over by HB. So overall, HA is going to win because of the resonance stabilization of the benzene ring that's connected to your alcohol. Next, we got a lot of choices. Here, this is a 5-membered ring that has 2 nitrogens, and each of those different spots, whether they're a nitrogen or carbon, has a hydrogen. And I've labeled those as HA, HB, HC, HD, and HE. Of those 5 different hydrogens, which of these is going to be the most acidic? Go ahead and pause the video and kind of make your guess. Now, for these, there's 2 general tiers. First off is going to be my HA and HC. Both of those are connected to a nitrogen, and being connected to a nitrogen is going to be way better than a carbon because nitrogen is going to be more electronegative than carbon. So A and C should be more acidic, and B, D, and E should be less. Now, between A and C, one thing that we see is the nitrogen that has HA attached to it is going to be net neutral, and it's going to have a lone pair, where the nitrogen on HC has 4 bonds to it, and it has a positive formal charge, because nitrogen wants 3 bonds, this one has 4. Now, when I see that positive charge, if I put a lone pair onto it, that's going to make that net neutral, where if I remove HA, I would put an extra set of lone pairs, so I'd have 2 lone pairs on that nitrogen, and that would end up making it a negative. So if I kind of imagine, let's get this pen active, maybe, there we are. So if I remove this one, I'd have a nitrogen, and then double bond, 2 sets of lone pairs, and then this still has a hydrogen, so this would have a plus charge, and this would have a minus charge. That's not the greatest structure because of all the charges. I now have 2 charges, a positive and a negative, where if I instead, zoom out just a touch, if instead I remove HC, I will still have this as NH, double bond, and here just 1, and then this would be a net neutral. Neutral is going to win out compared to charges stuff. So, and that's the same stability that we think about when we're thinking about resonance. So having that positive charge will definitely say that HC will be a lot more acidic than HA, because if I abstract HA, that negative charge pops on the nitrogen, where if I extract HC, I don't have any negative charges. So if you see stuff with charges, that's like a really nice hint. And for that, I would then think that HC would be the most acidic. Now, that is kind of a general rule of thumb, but you don't want to take it always. And I intentionally put this next example directly after this one to kind of prove that point. So if I look at this next one, let's zoom back in a little bit. I have an HA that's connected to a nitrogen that carries a positive charge. And in comparison, I have HB that is connected to my carboxylic acid. Now, based on the rationale that I used in the last one, if I abstract HA, that would give me a neutral structure, because that would be a lone pair on the nitrogen with 3 bonds, where if I abstracted HB, I would end up getting a negative charge that would do resonance. And interestingly, in here, HB is going to be your more acidic compared to HA. While you do have charges, if you abstract HB, the pKa is actually kind of your big descriptor here. The resonance stabilization is just overwhelming. So here, a pK of a carboxylic acid is around 5. If I look down at the pKa table, and I have kind of this kind of just like shortened version down here. So sp3, sp2, sp hybridized carbons, sp3 and sp2 are really high, way up in like the 45s and 50s, where my sp2 is down at 25. A normal amine is around 35, so that's pretty high. Alkyls are around 16, we talked about that. Our phenols, which are the OH connected to a benzene, is around 10. Carboxylic acids are around 5. And then down here, I have my 2 entries for my charge stuff. If you have a charge in an oxygen, that actually gives you a negative pKa, so that is incredibly acidic. So a charge in an oxygen, almost automatically going to be your number one most acidic. Interestingly, though, a charge on your nitrogen is actually going to drop it down a ton, but your original, if you look at your primary and secondary amine over on the left side, has a pKa way up at 35. So by putting a positive charge, you lower that a ton, but you only lower it down to 9. And 9 is not going to overcome the power of your carboxylic acid being around 5. So a protonated nitrogen is actually going to be less acidic than a carboxylic acid. Protonated oxygen, you can take it to the bank. But the protonated nitrogen is a little bit weird because of how high the pKa of your amines are. So in our kind of difference here, this is actually going to have a pKa of around 9. So it's actually not going to win out. I kind of do that just so you don't get automatically kind of like caught up in kind of like thinking about like some of our rules and stability. They work like 98% of the time, and that's kind of like why we go through them, but they aren't an automatic like surefire. There are some extra things that we do need to take into account. And one of the most common places where you do see it fail are going to be with your quaternary or those 4 attachment nitrogens. So those ammonium-like ions are acidic, but not as acidic as a carboxylic acid. And if it helps, carboxylic acid has a pKa around 5, and that's going to be like a group that we're going to see again and again and again, and is almost always going to win out. So hopefully that was some like nice extra practice on walking through thinking about a bunch of acidic protons. We'll go ahead and end the video here, and then in the next one, we're going to get a bunch of practice doing some acid-base mechanisms and thinking about like doing some like arrow pushing. So I'll see you in that one.